we're going to try to pick up lecture today where we left off the previous lecture. And if you recall, what we did is that we, from the first postulate of thermodynamics, developed the differential for the internal energy, which was TdS minus PdV. And then we had a definition, and we said, well, the Helmholtz potential A, we could define that as U minus Ts. And from there, we found the differential for the Helmholtz potential, which was minus SdT minus PdV. We also defined enthalpy as U plus PV. And from there, we were able to find the differential for enthalpy, that dH then is just TdS plus VdP. And then we also were able to define the Gibbs. And you could say, well, the Gibbs is either equal to H minus Ts or U plus PV minus Ts. And we found the differential for the Gibbs free energy as well. That's minus S dt plus VdP. And we were able to say then that after these transformations, we were able to change the sort of canonical independent variables for the energy. Or if you knew that energy as a function of those variables, you could calculate everything that you wanted to know thermodynamically. So the canonical variables are in the differentials. And so for the internal energy, the canonical independent variables are entropy and volume. For the Helmholtz potential, it's temperature and volume. For enthalpy, it's entropy and pressure. And for the Gibbs free energy, it's temperature and pressure. And that's one of the reasons why for phase equilibria, the Gibbs free energy becomes very important, because we make essentially all of our measurements as a function of temperature and pressure. And we also said you guys will get a little bit of practice in using these differentials in one of our future assignments, actually the next one. But we stopped at a point where we had these four differentials and said you'll practice using them. But we didn't talk about the fact that all of these differentials actually contain additional information that we've already used throughout this semester. And so what I want to do is to show how you can actually convert from these differentials. And from the differentials, we're going to derive Maxwell relations. And it turns out that we've already used the result of 3 Maxwell relations, or we've had 3 results that stem from Maxwell relations already in the semester. We're just doing the math sort of on the back end instead of doing the math on the front end, hopefully to make the material a little bit more accessible to everybody, okay? And so if we're gonna start deriving Maxwell relations, we have to start with any of the differentials. And since we're gonna take advantage of the fact that we can manipulate their canonical variables a little bit, we're gonna take advantage of a relationship really from multivariable calculus. And one of the things that hopefully that you remember from multivariable calculus is that the order that you differentiate a function does not matter. So, you might have written that in calculus as, let's say, d squared z dx dy equals d squared z dy dx. And maybe another way to write that that'll be a little bit clearer with what we're going to be doing today is that if I took d over dx of dz dy, that is equal to d over dy of dz dx. And we're going to use this to our advantage. And we're going to apply this rule from calculus to all 4 of our differentials. And the first one that I'm going to start with is the first differential that we derived in the previous lecture, which was the internal energy. And so we know that then the differential U, right, just as we wrote above, was TdS minus PDV. And what I'm going to do is take a derivative with respect to u for each of its canonical variables. And so what I mean by that is that I'm going to take du dv of du ds. And I'm going to take du ds at constant volume. And then I'm going to take d over dv at constant entropy. Okay? And we know then through this rule of calculus that that means that I could flip the order that I took this derivative, right? So this is d over ds of then du dv. And remember, I took du dv at constant s to the left, and I'm again going to take then ds at constant volume. And those two are absolutely equivalent to one another. And now I'm actually going to use the differential. So from the differential here, right, if I were to take du ds, that equals at constant volume, that just equals d over ds of tds minus pdv at constant volume. So of course at constant volume, that term goes away, and ds over ds is just equal to 1. So du ds at constant v just equals the temperature. And so that means that the left side of this equation simply becomes dt dv at constant entropy. Okay. And before I do the next one, is this okay? Does this make sense to everybody?
The math makes sense to me, but I'm kind of confused what the du over ds at constant v means, if that makes sense.
No, that makes total sense. So I guess the short way to explain this is, remember that we can have fundamental relations. And I showed an example at the end of lecture last time where you actually have a function of, you could have a function that is u equals u0 plus there'll be some integrals related to volume and some other stuff related to entropy in that function that you could derive from either statistical thermodynamics or from another pathway. So it literally is, in one sense, the derivative of a function. In another way, it's also asking an interesting question. Like du ds at constant v physically is really asking the question, if you had a rigid box, how would the internal energy change as the entropy changed, right? And if you think about it, what would the slope of that be? And the slope of that curve, right, as the internal energy changed with entropy in a rigid box, that slope would be equal to the temperature. And so there's a mathematical way to think about it, where it's really just taking the derivative of an equation. And the other one is that there's a physical explanation, right? These derivatives also have a physical meaning. Hopefully that helps.
Yes, thank you so much.
No, but that's a really good question, because I know we can get to doing these second derivatives on variables, and it ends up just being math, and you have no intuition for what the heck is going on. So that was a great question. All right, so if everybody's okay with the math, let's just do this to the opposite side, right? So this was that. So let's do this one a little bit over here. So this partial derivative then is just d over ds of, right? We're going to do this thing, right? So this just becomes d over dv of the exact same thing, right? Of of internal energy, right? So then this is TdS minus PdV, except this time we're doing it at constant entropy. And just like in the previous part of the problem, well, at constant entropy, that is 0. And then these dVs will cancel, right? dV over dV is 1. And so actually, then we can find that du dV at constant S is equal to minus the pressure. So then we get that dt dV at constant S equals minus dP ds at constant V. And this is our first Maxwell relation that we're going to derive today. Okay? And one of the nice things about Maxwell relations is that, yes, they're often used to associate or to find values given very difficult differentials, but they're also used to eliminate entropy a lot. And you're going to see that when we talk about applying Maxwell relations in a little while, that we're actually going to use these to get rid of these entropy-related derivatives. And hopefully that becomes a little bit clearer. All right, so we did U, and from the differential for U, we have our first Maxwell relation. And now we can do the exact same thing for the other energies. So here we have the Helmholtz potential, which is dA equals minus S dt minus PdV. And for the internal energy, remember we did derivatives based on S and V because those were the canonical variables. And here we're going to differentiate based on temperature and volume, which are the canonical variables for the Helmholtz potential. And if we do that, we have that d over dV of dA dt at constant V, and that's done at constant t, equals d over dt of dA dV at constant t, and that then is taken at constant V. And in the Helmholtz potential, right, so this term is like taking d over dt of minus S dt minus PdV at constant V. And this term over here is like taking d over dV of minus S dt minus PdV at constant t. And so on the left-hand side, right, we're taking this at constant volume. So dV is equal to 0. And then we have dt over dt, and those become 1. And so dA dt at constant V is just minus S. And so that gives us on the left-hand side of this equation, we have d over dV, or of minus S at constant t, equals, and now we'll do the same thing to the term that would populate the right-hand side. And at constant temperature, dt is equal to 0. And then dV over dV is equal to 1. And so this is just minus P. And so then d over dV at constant t of minus S is equal to d over dt of minus P at constant volume. And the last step here is that the negatives cancel. And we have ds dV at constant t equals dP dt at constant V. And that is our second Maxwell relation, right? We're going to get one for each energy. Okay. All right, does that make sense to you guys? Was that okay? Okay. So there's two more energies to do. The math is the same. So if you followed the math here, I'm going to assume that you can follow the math for the last two cases. And all I'm going to give you then is the result. So that way we can do a couple other things. So if DH is TDS plus VDP, right, you would take your derivatives as with entropy and pressure. And what you'll find from the enthalpy is that dt dp at constant s equals dv ds at constant p. And I just want to make sure that it's clear that those are partial derivatives. So that's our third Maxwell relation. And we also have dg is equal to minus s dt plus vdp. And here the canonical variables are temperature and pressure. So you would take the second derivatives with respect to temperature and pressure, just like we did above. And you would find that ds dp at constant t equals minus dv dt at constant p. And that would be the fourth Maxwell relation. Okay. And all of those were obtained from applying just that differentiation rule from multivariate calculus to the differentials that were derived in the last lecture. Now, before I do anything with them, I just want to stop and ask and if anybody has any questions.
So we're always taking the derivative with respect to the what was the word you used? Conical variables?
Yeah, the canonical variables.
Canonical variables.
Yep.
Okay, so whatever I guess the differentials are, like ds and dv, if we were doing du, would be the canonical variables, or like in dg, it would be dt and dp.
Yeah, that's right. So like for dg, here, right, we would be, this would be d over dp of dg dt at constant p, and that one's at constant t, equals d over dt of dg dp at constant t, like that. Yep. And
okay,
the canonical variables, are always in the denominator.
Gotcha. And when you say constant p, that's just because you're changing t, right?
That's right. And if you remember from multivariable calculus, right, if you're going to take a partial derivative, you're taking the derivative of that function with everything else held constant. And so we're just being consistent with that here. And also inherent in all of these in all these derivatives is that n is also equal to a constant. But because I use the intrinsic form, I wasn't explicit about the fact that the number of moles were also constant. But that's also true here. Gotcha.
I think my vector calc teacher just implied that those were constant and never used like subscripts. So thank you.
Yeah, I really do like to be explicit about it because sometimes when you're taking multivariable calculus that you have one function and you're only often interested in how maybe y changes with x or z changes with y. Here there's so many thermodynamic variables that we're trying to track. I really prefer to be very specific about what is being held constant, and that's why I'll have these subscripts. It'll also help us track it later when I give you a shortcut for a couple of other things. Now that we have the four Maxwell relations that we derive from the differentials, let's demonstrate how you can actually use them to learn about some of the systems that we've talked about in our class so far. And to me, the most obvious place to start is to ask what I think is a logical question is, how does this thing that we postulated existed, right? The internal energy. So how does that change with variables that we actually know something about, like temperature and volume, right? So let's try to answer that question. Okay, so how does the internal energy change with temperature and volume? Well, if you remember at the beginning of this course, when we were faced with a question very similar to that, we actually first wrote it as mathematically. We said, okay, well, that means that, we have some function of temperature and volume. And if we wanted to answer this question, we could just take the total derivative. And so then we would know that du would be equal to then du dt at constant v times dt plus du dv at constant t dv, right? And, we took this step, really early on in the semester, and we've actually used it to derive expressions for entropy and other things. Now, last time, we showed that this is an alternative definition for something that we've used in our class. Does anybody remember what that was?
It was the CV, right?
That's right. Yeah, that's an alternative definition for the constant volume heat capacity. And so, all right, we know then that du is then equal to CV dt plus du dv at constant t dv. So we're kind of left with this question of what in the world is du dv at constant t? And to answer that, we're going to use our differential first that we derived in the last lecture. So we know that du is equal to TdS minus PdV. So from this, du dv at constant t then just equals t times ds dv at constant t minus p times dv over dv at constant t. And of course, this dv at constant t is just equal to 1, right? So this just becomes equal to minus the pressure. And okay, this is fine. We know what the pressure is, or at least we feel like we know what pressure is. And that leaves us with a question of what in the world is ds dv at constant t? Well, this is why we derive the Maxwell relations. So ds dv at constant t is right here. We actually derived that is equal to dp dt at constant v. So we can insert that here. And then, oops, that's the wrong one. And then du dv at constant t then equals t times dp dt at constant v, right? That's the Maxwell relation, minus p. And so now we have an expression for du. So du is equal to cv dt plus t times dp dt at constant v minus p dv, right? And all I've done here is inserted this expression for dp dt, or for du dv at constant t, for this term that we had here. So the first thing I would like to say here is that this relationship that is now derived here is always true. We have not made any assumptions here. All we've done is ask a question, and we mathematically came up with a construct to answer it. So this is always true thermodynamically. So the reason I'm being very specific about that is that now from here, we can start to ask other things about specific systems. So I want to ask about an ideal gas, because we've said, at least in introductory thermodynamics, we're only going to stick with ideal gases. So let's make this assumption and see how this equation is going to simplify. Well, if we assume that it's an ideal gas, or if we're trying to understand how the internal energy changes with temperature and volume for an ideal gas, well, that means that du is CV dt plus T times dP dt at constant V. And for any gas, this derivative, dP dt at constant V, is where we're going to include our equation of state. And we know for an ideal gas that P, V equals RT, or P equals RT over V. So if we take this derivative, right, if we ask ourselves, what is dP dt at constant V? Well, if we take that derivative, right, dP dt at constant V of RT over V, that's just R over V. So then we have then du equals CV dt plus T times the result of that derivative that we just took, right? So that's just R over V minus P dV, right? And this just becomes du is equal to CV dt plus RT over V minus P dV. But if you look over to the right, what is RT over P? Or sorry, RT over V? That's just P. And so we end up with du is equal to CV dt plus P minus P dV. And of course, P minus P is just 0. So we have this relationship that du is equal to CV dt for an ideal gas. And this is the math behind our assumption this entire semester that the internal energy is only a function of the temperature, or that the change in the internal energy is only a function of temperature, because we've only been dealing with ideal gases, unless we're using the steam tables, of course, for steam. But for all of our equation-based problems, and we assume it an ideal gas, the internal energy does not change with anything other than temperature. And so we've used du equals CV dt, or delta U is the integral of CV dt this entire semester. And this is the math behind why we did that. And before I move on to the next thing, would anybody like to ask a question about what we did? No? Okay. So let's ask another question. We asked a question about the internal energy. Let's do the same thing for enthalpy, except as you know, in a lot of the problems we've been doing related to enthalpy for open systems, we know a lot about temperature and pressure. So let's also ask then, how does the enthalpy change with temperature and pressure? And we're going to do very similar math here, right? Because that's just us saying the enthalpy has to be then a function of temperature and pressure. So then dH equals dH dt at constant P dt plus dH dP at constant T dP. And in our last lecture, this was an alternative definition for what? Does anybody remember?
CP?
Yep, this time it's the constant pressure heat capacity. So now we know that dH is equal to CP dt plus dH dP at constant T dP. And just like in the previous example, we are now to figure out what is dH dP at constant T. Well, if you remember, our differential for enthalpy above was TdS plus VdP. And if that's the case, then dH dP at constant T equals T times ds dP at constant T plus V times dP over dP, which is just 1, just like it was in our previous example. And so now we have that dH equals Cp dt plus T times ds dP at constant T plus V dP. And this time, we're going to use the Maxwell relation from the Gibbs free energy to substitute here. And we said just a few minutes ago that that was ds dP at constant T equals minus dV dt at constant P. And so that means that dH is equal to Cp dt plus T times, or minus T, times dV dt at constant P plus V dP. And just like I said above, I'm going to be clear that this relationship is always true. Because just like the internal energy example, we haven't made any assumptions yet. We asked a question and mathematically derived an answer to it. So now let's make the same assumption that we made just a moment ago, and that we're dealing with an ideal gas. And so just like we did before for an ideal gas, now we want to find what dV dt is. So remember, for an ideal gas, PV is RT, or V equals RT over P. So then dV dt at constant P just equals R over P. And if we substitute that above, we have dH is equal to Cp dt plus minus then T times R over P, which is minus RT over P plus V dP. And of course, minus RT over P is just equal to minus V. So that means that dH equals Cp dt plus negative V plus V dP, or dH equals Cp dt, which is exactly what we've been using for an ideal gas this entire semester. Okay? All right, any questions about this one? I know the math is very similar to the internal energy. Okay, so let me do one more, okay? And then I'm going to give you something that hopefully helps you with remembering these things. So you remember it. You don't have to remember all the Maxwell relations and the differentials. Because quite frankly, even though I've been doing this a long time, even I don't bother to memorize all of them. Because using that tool, I can do it in a minute, as opposed to trying to recall a bunch of complicated stuff. All right, so here's what I'm going to do then. I'm going to prove that the constant volume heat capacity is equal to the constant pressure heat capacity for liquids and solids. Okay? So the way that I'm going to do this is there's actually two different ways to do it. I'm going to do it the easier way. And if anybody's really interested in the much more complicated way, we could do that some other time. But I'm going to do this by first saying, you know what? I know that entropy can either be explained as a function of temperature and volume, or that entropy can be explained as a function of temperature and pressure. And that means then I can describe the change in the entropy as then ds dt at constant v dt plus ds dv at constant t dv. And maybe I'll draw a line down the middle because I'm going to do these in parallel. Or I could say that, well, ds is equal to ds dt at constant p plus ds dp at constant t dp, right? That I don't have to be specific with the variables that I have because I know from the ideal gas law, right? If PV equals RT, if I know two of them, I know the other one. So I can either have this as a function of temperature and pressure or temperature and volume. I also could do pressure and volume, but I didn't do that here. All right, so if this is true, then ds then just equals, remember the definition for the constant volume heat capacity is T times ds dt at constant V. So that means that this first term is just CV over T times dt plus ds dv at constant T dv. And on the right-hand side, where I know this is a function of pressure, this is just Cp over T dt plus ds dp at constant T dp. Now, what I can do is substitute the Maxwell relations I know. And I know that ds dv at constant T equals dp dt at constant V. And I also know that ds dp at constant T from the Maxwell relations is equal to minus dv dt at constant P. In fact, I think these are the two that we just used. So if that's true, then ds is equal to Cv over T dt plus dp dt at constant V dv. And on the right-hand side, ds is equal to Cp over T dt minus dv dt at constant P dp. Okay? All right. So I'll throw this out to you guys. What is a very common assumption that you make for liquids or solids?
They're incompressible.
They're incompressible. Yeah, that's great. So if I assume that liquids and solids are incompressible, then the dv's go to 0. And what I'm left with is that ds equals Cv over T dt on this side, and that ds is equal to Cp over T dt on that side. And so that if Cv over T dt then equals Cp over T dt, of course, those cancel and those cancel. And you're left with, for liquids and solids that are incompressible, the constant volume heat capacity is equal to the constant pressure heat capacity. Okay, the last item I want to cover today is a shortcut to remember all of these things. And I actually just remember a sentence, and it is that very awesome thermodynamics undergraduate students have passed. And I remember that because we're going to end up taking each of these capitalized letters and we're going to put them around a square. So I'm going to draw a square. And we're going to start in the upper left-hand corner. So it's very awesome thermodynamics undergraduate graduate students have passed. Okay. And then the only other thing that I remember is that there are two arrows and they point towards the upper corners. And from this, I can get all the Maxwell relations and all of the differentials. And I'm going to do a couple examples of each here to show you how and to provide this as a reference so you guys can look back on it later. And let's do the differentials first. So one of the things that I want you to notice here is that if I look at the energies, the canonical variables are on the same side of the square as the energy, right? So remember, the canonical variables for the internal energy are entropy and volume, right? So they're right next to each other. And for the Gibbs free energy, right, they were temperature and pressure. And the temperature and pressure flank the Gibbs. So when I want to come up with a differential, the thing that I do is to pick one of them. So let's do the Gibbs. So the first thing that I do is I write dg is equal to, well, I know since they're on the same side as the square that there's going to be dt and dp. And you know that in all the differentials that s and t are linked and v and p are linked. So now the only thing that I do afterwards is I look where the arrow is pointing. So if the arrow is pointing towards the first term, it's positive. And if it points away from it, it's negative. So obviously we're pointing away from the S, so that's negative, and we're pointing towards the volume, and so that's positive. And if you look back in our notes, that was the differential for the Gibbs free energy. Let's do one of the other ones. Let's do the Helmholtz. So I know for the Helmholtz that dA then is equal to, I have the canonical variables flanking it. So I know that it's going to be dt and dv. And again, s and t are always related, and p and v are always related. And you'll notice that you're pointing away from the s and away from the p. So I know that the differential for the Helmholtz potential is minus s dt minus p dv. And let's do the same thing for u. So du is then equal to, right? I know it's dv and ds. And I know that that's always going to be pressure. That's always going to be temperature. And I'm pointed away from the p and towards the temperature. And the last one is the enthalpy. So dH, right, is ds and dp. And we know that we're pointing, or sorry, that this is TDS, this is VDP. And we know we're pointed towards temperature, which is positive, and we're pointing towards the volume, which is also positive. And that is how I remember all the differentials. I just remember very awesome thermodynamics undergraduate students have passed. I have two arrows, and I just remember that if you're pointing away, it's negative. If you point towards, it's positive. And that's how I get all of the differentials. Okay, so then let's do the Maxwell relations. All right, so.
Question. Before you move
sure.
On. So S is always coupled with T, and P is always coupled with V.
Correct.
Gotcha. Okay.
Yep. And actually, if you go back and look at all the differentials, that's true, right? And it just comes from the way that we've defined the temperature from the internal energy, as we talked about in the last lecture. And one way to remember that is, at least I used to remember it as, remember, work is minus PdV, right? And that's in du, right? So du has minus PdV in it. And so any transformation that we were to do from that point where we added plus PV or minus TS automatically links those variables together. All right, so the Maxwell relations are slightly more complicated, okay? But the way that I do a Maxwell relation is that I start at a corner of the thermodynamic square, okay? And I'm gonna make kind of an L shape. So I'm gonna go up and over. And what I do is I start in my initial corner and I write d whatever that corner is. So in this case, it's ds, right? Because I started here and I'm ending up here. And so I go from ds to v, so then I get ds dv, and I'm going to temperature. So this L shape that I made told me that I'm going to go ds dv at constant temperature. And to find a Maxwell relation, the next thing that I'm going to do is I'm going to flip these two inside of the derivative or inside the parentheses. So I'm going to get d over dt at constant volume. And the thing that you are missing here is the last corner, right? Which in this case is the pressure. So that becomes dp dt at constant v. And now the arrows tell me positive or negative again. So the arrow is pointing away from S, right? So I know that that's negative. And it's also pointing away from P. So that's negative. And so those negatives cancel. And so we get that ds dv at constant t equals dp dt at constant v. And remember, that's exactly the Maxwell relation that we found from the Helmholtz potential, that ds dv at constant t equals dp dt at constant v. All right, I'm going to do one more because I know that one is way harder for people to remember than the first one. And so let's do, let's just go the other way. All right, so I'm going to go this way then, and I'm going to start here and go up. So if I do that, remember, I'm going to start here and go to there. So that tells me that I have ds dp at constant t equals, and the first step here is to flip the p and the t, or the 2 in the denominator, right? So then this would be d over dt at constant p, and you fill in the missing corner, right? And so then that becomes volume. And now you're pointed away from the S and towards the V. So we get that ds dp at constant t is equal to minus dv dt at constant p, which we just used a moment ago, right? That is the relationship that you get from the Gibbs free energy, right? That ds dp at constant t equals minus dv dt at constant p. We could do the other ones as well. And while we're here, we might as well do them, okay? So the next Maxwell relation that I will do is, let's start up here and go down to there. And if we do that, we know that then we get dt dv at constant s equals then some d over ds at constant v of the missing corner, right? Because we have we have 3 of the 4 corners here, right? And that becomes dp ds. And we know that we're pointed towards the temperature and away from the pressure. So dt dv at constant s equals minus dp ds at constant v. And that was the Maxwell relation that we got from the internal energy. Okay. All right, and let's do one last one. And this is obviously not something I expect you to perfect just during our discussion today. So now let's go back this way, right? the opposite of what we did the second time. And so now I have dt dp at constant s equals d over ds at constant p of the missing corner. So we have, right, temperature, pressure, entropy. So the missing corner is the volume. And I know I'm pointed towards the temperature and towards the volume. So they're both positive. And this is the Maxwell relation that you would get from the enthalpy, or for the differential for the enthalpy. And so you can see from this sort of simple tool, we can actually get both the differentials and the Maxwell relations. And I get them all by just remembering that very awesome thermodynamics undergraduate students have passed.